So let's talk more about our horizontal asymptotes that come up with rational functions. So that's what we're going to be describing when we go to describe the long-run behavior. What we can use is the horizontal asymptote. Now, with this, so like we talked about in the last video, long-run behavior is where you describe as x goes to negative infinity, what is our function doing, in this case a rational function. As x goes to positive infinity, what is our function doing, in this case a rational function. And if we have a horizontal asymptote, then this is going to be a number. So like I said in that last video when we dealt with polynomials, it was going off to positive infinity or negative infinity. When we have a horizontal asymptote, that should be a value that our function's approaching in the long run of our graph. Now, finding this horizontal asymptote is a bit more tricky than finding our vertical asymptote, which we'll talk about in the next video. With the horizontal asymptote, there's going to be a few rules to look at. And what we'll go through is each of these rules and some examples below. What we need to think about is our rational functions made up of the division of two polynomials. So we have our numerator p of x, and we have our denominator q of x. In order to figure out what our horizontal asymptote's doing, we run a comparison of the degrees of those two polynomial functions. So what we're going to have is a letter m is going to be the degree of our numerator, and n is going to be the degree of our denominator. So again, the degree is going to be that highest exponent. So we want to compare those two numbers. As we can see, we are going to have a list here of if the degree of the numerator is smaller than the denominator, if they're equal, if the numerator is larger, and then we'll have kind of the special case of if the numerator's degree is exactly one more than the denominator, something kind of special happens. We'll look at a graph with it, but we're not going to work on actually calculating it. So just to read through these kind of quickly, but we'll look at examples dealing with each of these. So if the degree of the numerator is smaller than the denominator, then the horizontal asymptote is just y equals 0. So we'll have a horizontal asymptote along the x-axis. If the degrees are the same, then we're going to have a horizontal asymptote of y equals c, and c is going to come from the division of your leading coefficients. So that can be kind of tough to understand in words, but we'll look at an application. I'll be sure to refer back to this. If the degree in the numerator is larger than the denominator, then no horizontal asymptote exists. A special case of this scenario, in fact, these tie together. If the degree of the numerator is larger than the denominator by exactly 1 degree, then we have this thing called an oblique asymptote. So it isn't horizontal, it isn't vertical, it's going to be a special line that shows up. So we'll look at an example with that, but like I said, we're not going to go into calculating the oblique asymptote. So let's look at some examples with this. So for each of these, we're going to determine our horizontal asymptote. So thinking about the degree of the numerator, which we'll call m, and the degree of the denominator, which we're calling n. So I'm looking for in this, we'll talk about in another video, I can't remember if it's the next one or not, but what to do when we have a factored form. But in this video, if it's just all multiplied out, what we're looking for is our highest exponent. So in the numerator, it's going to be an exponent of 1 on our variable. In the denominator, we have this exponent of 2. So in comparing these, this is the case where if we compare these numbers, m and n, m is smaller than n. So with that, if I go to my cases up here, this would be my first case. So if n is smaller than n, then the horizontal asymptote is y equals 0. So if I'm looking for the horizontal asymptote, and I need to describe it. So it's going to be a line of y equals, and then our value is 0. So let's look at how this comes up on the graph. And I am going to put just a little visual for us here so we can see it. But what I expect from this information is having this line that's helping determine the long run behavior of my graph along that x-axis. So I've actually already graphed this one in the calculator here. So there's our 5x plus 1 over 10x squared plus 6x. So what I can see is we do have these, looks like 2 vertical asymptotes, but in terms of horizontal, that's our line coming through here. So let me go ahead and transfer that over into a little sketch here so we can talk about it. So my graph, I had kind of this piece, and then something kind of like this, and then this. So very rough sketch. And that goes on forever there. Okay, so we're not talking about vertical asymptotes yet because that's going to be our short run behavior, but what we're looking at is what's happening out here. And what our graph is doing is it's going closer and closer to 0 at those ends. Now, like I mentioned in the last video, and something to keep in mind, so our vertical asymptotes, those are lines that we can never cross. Can never cross those. As we can see here, we can cross the horizontal asymptote. That's completely fine. It's a behavior that's in the short run behavior of the graph. So in here we can cross and do whatever, but it's out here at positive infinity and negative infinity that we're getting that approaching that value of 0. So vertical asymptotes we cannot cross. Horizontal asymptotes we can cross. It's just when we get out to the infinities, it should not be crossing over. All right, so there's our first scenario. So just comparing the exponents on x of our leading terms for those polynomials, and if the numerator is smaller than the denominator, it's just y equals 0. Now this next case, we're just changing this a teeny tiny bit. So for our numerator, now we have x squared, so now this is degree 2, and for the denominator, it's still, that didn't change at all, so that's still degree 2. So if we compare our two values, they're equal to each other. So this is our second case. Like I said, the wording's a little tricky here, but basically our horizontal asymptote's going to be a number, and it's going to be a real number that we're working with, and it's determined by the ratio of the leading coefficients. So our leading terms, if we find those first, so the leading terms is where we got our degree. So that 5x squared is our leading term, and the 10x squared is our leading term. So we want to create a ratio of those numbers, and it's set up for us already. We have our numerator of our leading coefficient of 5, denominator leading coefficient of 10. So for finding our horizontal asymptote, what we'll have here is y equals, and we're taking 5 divided by 10, which is, if we reduce that down, 1/2. So we're going to have this horizontal line at positive 1/2. So again, I'm just going to make a sketch so that we have a visual to refer back to. Well, I can imagine if I set up a scale of 1, 2, we're going to have this horizontal line at 1/2 that we're approaching in the long run of our graph. So if I change this to 5x squared, here I have my graph, and if it even helps, you can always graph your horizontal line, so y equals 1/2. So over here on the left-hand side, what I can see is I have my graph, there's some vertical asymptotes in here, but horizontally, we're getting closer and closer to that 1/2 in the long run. This parabola here just goes off to infinity, so that's not using our horizontal asymptote at all. Notice on this right-hand side here, we do cross over, but it kind of comes back. it's not kind of comes back. The graph comes back to our horizontal asymptote and in the long run approaches it. So these are kind of the different ways that we can see our horizontal asymptote come up. Is we have some vertical asymptote, so we could just approach it without ever crossing it in the long run. We can have these pieces that typically come up in the middle that don't even use our horizontal asymptote because they're going off to infinity. And then what we had at the end here was something that came from our vertical asymptote. It crossed over, but then it's coming back to approach that value in the long run of our function. So again, just short run behaviors in there, and it can kind of do whatever it needs to, but then in the long run we're using that y equals 1/2 for our values for our long run behavior. All right, our next example here. So in the numerator, we now have degree 3 because of that 5x cubed. In the denominator, the 10x squared, it's still degree 2. So comparing these to each other, we have m, and comparing to n, we're seeing m is larger. So this is a case where we have no horizontal asymptote. But this is a special case. If we needed to describe the type of asymptote that we do have, this is the case where the value for the numerator is exactly 1 more than the denominator. So what we do have is called an oblique asymptote. And like I said before with this one, we're not going to calculate this. But just visually, I want to show you what it means. So, just to get kind of a little sketch going, what's going to happen is we're going to have this asymptote. It's not horizontal, it's not vertical. It's going to go like this. So it's actually a linear equation that comes out for our asymptote. So let's see what happens. Get rid of that and change that to an exponent of 3. What we can see is we have this kind of diagonal barrier here for our function in the long run. So it isn't just approaching a single value, it's like it's approaching an equation of a line, which gets pretty tricky. So that's what oblique will look like, is in the long run, it looks like it's going to negative infinity and positive infinity, and it technically is, but really it's approaching this linear equation that's going through there. So what we're seeing there is something like this. And then we can kind of cross over with that short run behavior. And then over here, something similar, but it's getting closer and closer to that line in the long run. So that's our oblique asymptote. Our last case here, so in the numerator, degree 4. In the denominator, degree 2. So if I compare those, m is larger than n. So we would have no horizontal asymptote. And this doesn't even have the relationship that we just saw in the previous example, because it's not, if I try to compare it to n plus 1, it's not just 1 more than the denominator, so it's not oblique either. So let's look at what this graph looks like and what it looks like to have no horizontal or oblique asymptote. So if we change that to 4, what we can see in terms of long run behavior is, for this case, we're just going off to positive infinity. It's not approaching an equation of a line, it's not approaching a single value. This is kind of the case that we saw with our polynomials. While this is not a polynomial because of those vertical asymptotes coming through, we would write our long run behavior in terms of going off to infinity. So that's what it would look like to have no horizontal or oblique asymptote.